Somewhere, on a day with no name, in a place we cannot point to on any map, a human being opened their mouth and said something. Not a grunt, not a warning cry, not the sound an animal makes when it's afraid or hungry or in pain. A word, maybe even a sentence, an idea carried on breath, understood by another mind. And then it was gone, forever. Here's what should stop you cold. In the entire fossil record of our species, there is not one single physical trace of that moment. No recording, no transcript scratched into stone. Voices don't fossilize. Sentences don't turn to sediment. Somewhere in our past, there was a first speaker, and we will never recover their name, their face, or the exact sound they made. But here's the strange part. We're not completely in the dark, because that moment left fingerprints, not on stone, not on bone, on us, buried in our genes, hidden in the shape of a tiny bone in the throat, scratched, quite literally, into pieces of ochre left in a cave in South Africa. Even carried, some scientists argue, in the calls of laboratory mice bred with a single altered human gene. Tonight, we're going to follow those fingerprints across 2 million years of human evolution. We're going to do something that sounds almost impossible. Hunt for the birth of language itself, using nothing but bones, genes, and scratched-out patterns on rock. And I need to be honest with you before we start. Nobody can hand you a date. Nobody can hand you a name. What we have is a set of clues, and a community of scientists arguing, fiercely and in good faith, about what those clues actually mean. So think of yourself less as a viewer tonight, and more as a detective walking into a 2-million-year-old crime scene, where the only witness never left a statement. Here's a fact that sounds obvious until you really sit with it. Talking is hard. Not emotionally, mechanically. To say a single sentence, your brain has to fire off a symphony of instructions. Your lungs, your diaphragm, your vocal cords, your tongue, your lips, all coordinated in fractions of a second, precisely enough to shape raw breath into meaning. Most animals on Earth simply don't have the anatomy for it. Their throats aren't built right. Their brains aren't wired for it. So if we want to find the first speaker, the first thing we need to find isn't a word. It's a body capable of producing one at all. In most mammals, the larynx, the voice box, sits high in the neck, almost directly behind the tongue. That's actually the safer design. It lets an animal breathe and swallow water at nearly the same time without choking. Human infants are born with their larynx in that same high, safe position. But sometime in early childhood, something unusual happens. The human larynx drops. It descends lower into the throat, creating a long, flexible chamber above the vocal cords. Space the tongue can move through in ways no other primate's tongue can. That extra space is what lets us shape the distinct vowel sounds, the ah, the e, the o, that make spoken language possible. It's also, evolutionarily speaking, a strange trade. That lowered larynx increases the risk of choking on food for every single human being for our entire lives. Evolution rarely keeps a dangerous trait around unless it's paying for itself many times over. Whatever we gained from being able to speak, apparently, was worth the risk of choking on a piece of bread. To find out how far back that trade-off goes, scientists don't just study skulls. They study a single, unassuming little bone called the hyoid. The hyoid is one of the strangest bones in your body because it doesn't touch any other bone at all. It floats in your throat, suspended by muscle and cartilage, anchoring the muscles that let you swallow and speak. In 1974, in the Afar region of Ethiopia, paleoanthropologist Donald Johanson and his team uncovered the partial skeleton of a 3.2 million-year-old hominin, Australopithecus afarensis, nicknamed Lucy. Lucy walked upright. Lucy's hips and knee joint prove it beyond serious dispute. But Lucy's skeleton didn't preserve a hyoid bone. and her brain case was barely a third the size of a modern human's, closer to a chimpanzee's than to ours. So could Lucy speak? The honest answer is almost certainly not. Not in any sense we'd recognize. She may have had calls, gestures, maybe even a rich social world built on sound and expression. But the biological hardware for shaped, flexible speech appears to be missing. Bipedalism came millions of years before anything resembling a modern voice. That gap between walking upright and talking is exactly why scientists had to look for a body built more like ours. And it took over 2.5 million more years of evolution to find one. And that search takes us to a bone belonging to a much later, much larger-brained relative. Creatures like Homo heidelbergensis, living roughly 600,000 years ago. When scientists study the hyoid bones and skull bases of heidelbergensis fossils, they find something startling. The shape is close to ours, unsettlingly close. Combined with changes in the base of the skull, a subtle downward curve linked to a repositioned larynx, and evidence of enhanced diaphragm control visible in the width of the spinal canal, some researchers argue this means heidelbergensis had something close to a modern vocal apparatus, hundreds of thousands of years before Homo sapiens even existed as a species. But here's where our first real twist comes in. Having the equipment to speak is not the same as having something to say. A pig, believe it or not, has a hyoid bone shaped remarkably like a human's. So does a red deer. Anatomy alone can be misleading. Plenty of species evolved similar vocal hardware for entirely different reasons, from mating calls to alarm signals, with nothing close to grammar behind any of it. So a good throat is a start. It's not proof. And that gap between capacity and use is going to haunt this entire investigation, chapter after chapter. Which brings us to our closest, strangest relatives. The ones who almost certainly had the equipment, and who spent decades being dismissed as if they never had a chance. For most of the 20th century, Neanderthals were painted as the dumb cousins of the human family. Hunched, grunting, practically wordless, a caricature that made its way into cartoons, textbooks, and casual insults alike. The evidence tells a very different story, and it's worth understanding exactly how that old caricature got built and dismantled. Early Neanderthal reconstructions were based partly on a badly arthritic, elderly skeleton found in France in 1908, whose curved spine and bent knees were mistaken for the species' natural posture, rather than the ravages of disease and old age. For decades, an entire species was judged by one unlucky, unhealthy individual. Later discoveries corrected the record. At a cave called Kibara in Israel, archaeologists found a nearly perfect Neanderthal hyoid bone in 1983. When scientists ran detailed mechanical stress loading analysis on that bone, testing how it would have handled the pull and pressure of speech-related muscle movement, the results looked almost identical to a modern human hyoid's behavior under the same forces. Their inner ear structures, too, are tuned to catch a very specific range of sound frequencies, and that range lines up remarkably well with the frequencies of human speech. If the bones hinted at speech, one gene turned that hint into a genuine scientific story, and it began, unexpectedly, with a single family in London. In the 1990s, researchers studying a British family, known in the scientific literature as the KE family, noticed something striking. Roughly half its members, across 3 generations, struggled severely with speech and grammar, despite normal hearing and normal general intelligence. In 2001, geneticists traced the cause to a single mutated gene, FOXP2. FOXP2 isn't the language gene. No single gene could build something as layered as language. But it's a master regulator, switching dozens of other genes on and off during brain and vocal tract development. Damage it, and fine motor coordination for speech collapses. Here's the detail that should give you chills. When scientists later sequenced Neanderthal DNA, they found the exact same human version of FOXP2. which means this genetic change was already in place in the shared ancestor of humans and Neanderthals, over 400,000 years before our two lineages ever split apart. That Neanderthal genome, first fully sequenced in 2010 by a team led by Svante Pääbo, work that later earned him a Nobel Prize, revealed something else almost nobody expected. Neanderthals and early Homo sapiens interbred. Most people alive today outside sub-Saharan Africa carry somewhere between 1 and 2% Neanderthal DNA. That single fact quietly demolishes the old cartoon. You don't interbreed repeatedly across a species boundary with a creature so cognitively different from yourself that it can't communicate. Something was being negotiated between these two populations: trade, kinship, conflict, cooperation. All of it, almost certainly, required some shared channel of meaning. So, did Neanderthals talk? Some scientists look at all this and say yes, almost certainly, they had genuine capacity for speech. Others urge caution. We are standing once again at that same gap: capacity and use. To close that gap, we need to stop looking at bodies and genomes belonging to our relatives and start looking at what's unique in ours. In 2025, a very different kind of clue emerged. Not from a fossil, not from an ancient genome, but from a second gene, one far less famous than FOXP2, called Nova1. Nova1 helps control how brain cells process genetic instructions during development. It's involved in something called RNA splicing, essentially deciding which parts of other genes' instructions actually get used. Researchers found a version of Nova1 that appears to be genuinely human-specific, present in modern humans but absent from the Neanderthal and Denisovan genomes tested so far. To test what that variant might actually do, scientists engineered it into mice, swapping the mouse version of Nova1 for the human one, and then listened. Mouse pups communicate with their mothers using ultrasonic calls, far above human hearing range but fully recordable with the right equipment. The humanized mice produced measurably different vocalization patterns than ordinary mice. Now, a real note of caution here, because this is exactly the kind of finding that gets wildly exaggerated the moment it leaves a research paper. This is a mouse study. Mice do not have language, and altering one gene didn't give them any. What it does suggest is that, on a molecular level, something in the machinery underlying human vocal communication may be genuinely unique to our species, a thread worth pulling, not a conclusion to lean on. And scientists chase threads like this for a reason, because sometimes, when enough of them are pulled at once, from completely different directions, a pattern starts to emerge that no single thread could show on its own. In that same year, one research team tried something almost nobody had attempted before. Instead of digging for bones or sequencing ancient DNA letter by letter, they went looking for the birth of language inside the branching structure of our own family tree. Here's the idea behind this approach, and it's genuinely elegant. Their DNA slowly drifts apart too, accumulating small differences generation after generation, like two branches growing away from the same trunk. If you study those genetic branch points carefully enough, comparing variation across dozens of present-day human populations, you can estimate roughly when those populations parted ways, a genetic clock of sorts, ticking silently inside every living person on Earth. In 2025, a research team led by Shigeru Miyagawa at MIT used exactly this method, but pointed it specifically at genetic variants linked to language-relevant cognition. Their conclusion was bold. The underlying cognitive capacity for language, they argued, was already present in Homo sapiens by at least 135,000 years ago, tens of thousands of years before most of the archaeological evidence we're about to look at. They suggested language may have existed first as a private, internal system, long before it was ever spoken aloud to another person. Only later, they argue, sometime around 100,000 years ago, did it spill outward, becoming something explicitly social and shared. This is one hypothesis, built on a genuinely novel method, and it has not become settled scientific consensus. Other researchers are actively testing it, challenging its assumptions, and proposing competing timelines using different genetic markers. That disagreement isn't a weakness in the story. That's what real science looks like while it's actively happening, in real time, argued out in journals most of us will never read. But notice something remarkable about that number, 100,000 years ago. Because that's almost exactly when the ground itself started talking. On the southern coast of South Africa, overlooking the Indian Ocean, there's a cave called Blombos. Inside it, archaeologist Christopher Henshelwood and his team found something in 2002 that stopped the entire field of human origins in its tracks. Pieces of ochre, a soft, reddish, iron-rich stone, deliberately engraved with geometric patterns. Dated to roughly 77,000 years ago, with an entire ochre processing toolkit, grinding stones, mixing containers made from abalone shells, ochre residue, pushing the site's earliest activity back closer to 100,000 years. Not far away, at Deep Kloof Rock Shelter, archaeologists found ostrich eggshell fragments engraved with strikingly similar, cross-hatched patterns, dated to over 55,000 years old, meaning this wasn't a single artist's one-off idea, but a tradition, repeated across generations, in a recognizable style. And at sites across the region, tiny shell beads, deliberately pierced and worn smooth from stringing, dating back roughly 100,000 years. Jewelry, essentially. Worn on a human body for reasons that had nothing to do with survival and everything to do with meaning. A symbol is a strange kind of technology. It's a mark that means something beyond itself. A shape that carries an idea out of one mind and into another, across distance and across time. Imagine the moment itself. Someone sits at the mouth of a cave, ochre stone in hand, and begins cutting a repeating pattern into its surface. Not randomly, but deliberately. The same shape, again and again. For that act to mean anything at all, there has to be someone else who will look at those lines later and understand. You cannot accidentally engrave a repeating geometric pattern. Someone had to hold an idea in their mind, and then choose specific marks that would carry that exact idea into somebody else's mind. Genomic modeling. Language possibly becoming social around 100,000 years ago. Physical evidence of symbolic behavior in the archaeological record. Exploding at almost exactly the same moment on a different continent using a completely different method of investigation. Two entirely different kinds of evidence. One written in the drift of DNA across generations. One carved into stone by an actual hand, arriving independently at roughly the same chapter of the human story. That is either an extraordinary coincidence, or it's the closest thing to a smoking gun this 100-year-old mystery has ever produced. So, case closed? Not so fast. Starting in the 1960s, researchers began raising chimpanzees alongside human infants, teaching them sign language, or symbol boards, hoping to find out just how close our closest relatives could come to genuine language. A chimpanzee named Washoe learned over 100 signs. A bonobo named Kanzi learned to use symbol lexicograms and appeared to understand spoken English requests with real sophistication. But in the 1970s, a project involving a chimpanzee named Nim Chimpsky, a deliberately ironic name aimed at linguist Noam Chomsky, became one of the field's most sobering case studies. After years of training, careful video analysis by psychologist Herbert Terrace revealed that Nim's longer sentences weren't grammar at all. They were mostly repetition and imitation of his trainer's most recent signs, strung together for reward, not for meaning. Chimpanzees, it turns out, can learn symbols. What none of them have ever reliably demonstrated is recursive grammar, the ability to nest ideas inside other ideas, endlessly, the way a human child does by the age of 4 without any formal teaching at all. Some linguists, like Daniel Everett, argue the roots of language go back much, much further than any of the evidence we've covered tonight. potentially into Homo erectus over 1 million years ago, based on that species' long-distance migrations and sophisticated stone tool traditions. Others, in a tradition connected to Noam Chomsky, argue language wasn't gradual at all, that it arrived as a sudden, singular cognitive leap, unique to our species, rewiring the mind almost overnight in evolutionary terms, perhaps triggered by a single genetic mutation that allowed the brain to combine ideas recursively for the first time. And even the shape of that first language is contested. Some researchers believe it began as gesture, hands and faces speaking before voices did. An idea supported by the fact that both humans and apes share far more overlapping brain circuitry for controlling hand movement than for controlling vocalization. Others picture something closer to song, a flowing musical prosody that only later split apart into words on one side and music on the other. A theory that finds unexpected support in how human infants respond to the rising and falling pitch of a caregiver's voice long before they understand a single actual word. Still others believe language was never really for communication at first, evolving instead as a kind of social glue, replacing the physical grooming our primate ancestors relied on to hold together social groups that had grown too large for one-on-one bonding. Gradual or sudden, gesture or voice, private thought or social bond or social glue. Every one of these is a serious theory, defended by serious scientists, and not one of them has won. Think about that for a moment. Somewhere in the deep, unrecorded past, a single human being said something and changed the trajectory of an entire species. Every story ever told, every promise, every "I love you," every lie, every joke, every prayer whispered into the dark, all of it traces back to that one unrecoverable moment. We will never know their face. We will never know their voice. We will never know their name. But we carry a piece of them every single time we open our mouths and turn breath into meaning. Every time a parent names a child. Every time two strangers negotiate a price. Every time someone anywhere on earth says, "I understand." So here's the question I'll leave you with. The one nobody can fully answer, not the linguists, not the geneticists, not the archaeologists still digging through the dirt of Blombos Cave. If you could go back to that exact moment, the very first sentence ever spoken by a human being, what do you think they said? Tell me in the comments below.